Hi friends, myself Shubhanshu and today I with my friend Shobit will be discussing about heat transfer in solid oxide fuel cells. Talking about solid oxide fuel cells, they are high temperature operating devices which converts chemical energy of fuels directly to electrical energy in an environmental friendly manner as there is no toxic element or contaminant leakage. Also fuel cells are efficient as they are not limited by Carnot efficiency which most conventional energy generation setups are limited to. Their operating temperature ranges lie between 500 to 1000 degrees Celsius. In fact, classification of SOFC depending upon operating temperature range is also done. SOFC consists of two porous phase, cathode and anode, a dense ceramic electrolyte, and an interconnect. As can be as can be seen, all constituent phases are in solid state, hence the name solid oxide fuel cell. Fuel cells are limited by their design, operating temperature and transport phenomena associated with it. So its theoretical efficiency lies between 60 to 80%. Comparing SOFC with other fuel cells, they are attractive in the sense that they are fuel flexible as variety of hydrocarbon fuels can be used since they are CO tolerant, which means that voltage loss occurs at high carbon monoxide concentration. Also, these cells are advantageous as due to higher operating temperature, waste heat is of high quality and can be utilized for further heat and power generations. However, high operating temperature is a con as well, since it limits mass production of SOFC due to shortage of material which can easily be operated at these temperatures. Also, its thermal control becomes difficult and it requires long starting time as well. Now, talking about the constituent of SOFC. First is electrolyte. Most widely used electrolyte is yttria stabilized zirconia. It's majorly due to this ceramic material that SOFC are operated at high temperature. Since above a particular temperature, they only conduct oxygen ion and non-conductive to electron, thus behaving as a perfect electrolyte. Moreover, they also show catalytic effects to both chemical reaction taking place in this fuel cell. Talking about anode, commonly used material is nickel yttria stabilized zirconia cermet. At anode, diffuse oxygen ions from electrolyte are used to oxidize hydrogen fuel. Basic property associated with anode is that it should be porous so that fuel can easily be transmitted to anode electrolyte interface. Generally, steam reforming reaction takes place in anode support layer of fuel cells and will be discussed later in this video. Another porous constituent commonly used is lanthanum strontium manganite, which act as cathode in our fuel cell setup. It's majorly used due to its compatibility with yttria stabilized zirconia, as coefficient of thermal expansion of these two are nearly equal, thus limiting stress buildup. However, it is ionically bad conductor and so electrochemically active reaction is limited to triple phase boundaries. Triple phase boundaries is basically region where electrolyte, electrode and fuel gas meet, and triple phase boundaries are present on either side of electrolyte. Further, there is one more component of fuel cell, interconnect, which connects each cell in series to sum up individual electricity generated. They must possess properties like high electrical conductivity and stable under high temperature oxidizing and reducing environment. Hence, most commonly used interconnects are nickel and steel based alloys. Here's a demonstration how things work in SOFC. As you can see, there's electrode and electrolyte setup in between and fuel coming from anode side and pure O2 coming from cathode side. At cathode side, O2 reduces to O minus 2 and this ion then diffuses through electrolyte and reacts with incoming H2 fuel at anode to give water which is flowing down and electrons. This electron passes through external circuit to produce electricity. Chemical reaction occurring in fuel cells are major heat generation sources. Hence, it's important to discuss what kind of reaction are occurring in cells. Basically, three kind of reaction occurs in SOFC. Steam reforming reaction. Here's in this video, I've shown you methane steam reforming reaction. Basically, methane reacts with water to give carbon monoxide and hydrogen. Then is water gas shift reaction. This is hydrolysis of carbon monoxide and gives CO2 and H2. The last one is electrochemical reaction, which is general redox reaction, which includes oxidation of H2 to H plus and O2 gas to O minus 2, as you can see. Basically here, two main reactions are steam reforming reaction and electrochemical reaction. The water gas shift reaction occurs as a side reaction due to the byproducts from the other two reactions and the prevailing temperature conditions of the fuel cells. Talking about enthalpies of these reactions, steam reforming reaction is highly endothermic. As can be seen, its enthalpy at 1000 degrees Celsius is about 227.6 kilojoule per mole, and hence it acts as a sink of heat in the fuel cell. The other two reactions are exothermic. The corresponding values are for water gas shift reaction, it is minus 31.8 kilojoule per mole, and for global electrochemical reaction, it's at 1000 degrees Celsius, it's minus 250 kilojoule per mole. Here's a general schematic of SOFC. As can be seen through lower part in anode, methane steam reforming and water gas shift reaction occur at anode support layer. Further, fuel side electrochemical reaction occur at anodic triple phase boundaries shown in between shown in the middle zoomed box, while air side electrochemical reaction occur at cathodic triple phase boundaries shown in the top zoomed box. Talking about why heat transfer analysis is important. Because as discussed, though they are better and reliable source for producing electricity, their mass production is limited due to higher manufacturing cost, which is the consequence of high operating temperature. However, as we decrease operating temperature, other phenomena like chemical reaction associated also get affected. Hence, heat transfer analysis are of acute importance for this fuel cell modeling. Talking about modes of heat transfer, all general modes, conduction, convection, and radiations, are significant for SOFCs. Convection occurs between flowing gas and solid surfaces. Conduction takes place in solid and in porous part of SOFCs, and radiation occur from stake to surrounding and surface to surface within air and fuel channels. Firstly, general equation related to conduction and convection will be discussed, and due to additional complexity, radiation will be explained in details by Shobit later in this video. Steam reforming reaction is kinetically more favorable than electrochemical reaction. Also, as we discussed, it acts as a sink due to endothermic process. Hence, a temperature gradient is developed in the fuel cell, which further causes thermal stress and reduces the efficiency of the fuel cell. General heat conduction equation to calculate temperature distribution in solid and gas phases in porous electrode is shown here. Qs is the heat source. In the first expression, Qs is the heat source which contains all terms of heat generation, which includes polarization and chemical reaction generation of heat. Second term on right side in gas phase heat conduction equation implies heat used due to increased temperature of gas, thus reduced from net heat generation term. Both these equations are based on local temperature non-equilibrium model, where the temperature from gas and solid phases are not assumed to be locally the same as assumed in local temperature equilibrium model. The last equation here represents heat transfer between gas and solid phases, and it accounts for the convective mode of heat transfer in the fuel cell. And its general equation as heat transfer in convection is given by H into delta T, where H is the coefficient of heat transfer. Coming to the heat absorbed or consumed by steam reforming reaction, this equation represents per volume heat generation. Here RMSR denotes rate of reaction and delta H MSR represent enthalpy of reaction. As we can see, for different temperature range operation of fuel cell, different rates for steam reforming reaction can be considered from the table given below. Now moving on to heat generation by water gas shift reaction. The expression is similar to that of steam reforming as can be seen. Here also RWGs represent rate of water gas shift reaction given by expression below. Heat associated with electrochemical reaction is generated at both electrodes and in different amount. Therefore, one should take into account entropy changes for each semi-reaction of redox reaction, which can be calculated from thermodynamics relation delta G equals to delta H minus T delta S. Here, change in Gibbs free energy represent maximum work that can be obtained. Now from this, heat generation per unit volume can be calculated using the second expression shown below. Using this equation, we assume that reaction sites are made up of infinitely thin layers. There is another process via which heat generation occurs in SOFC, which is polarization. It is basically losses in voltage due to imperfection in material microstructure and design of fuel cells. They are of three kinds: concentration polarization, activation polarization, and ohmic polarization. First, talking about concentration polarization. It is polarization associated with variation of concentration of critical species due to mass transfer process. Heat generation per unit volume is given by the expression shown at last. Here eta in general accounts for polarization effects. Second is activation polarization, which is extra potential needed to overcome energy barrier of rate determining step to value that reaction proceeds at a desired rate. Heat generated per unit volume is given by expression shown. Also, relation of current density is given in this slide. Last type of polarization is ohmic polarization, and it is due to resistance to ion transfer through electrolyte, yttria stabilized zirconia, electron transfer through electrodes, and current collectors, and also by contact resistance between different cell components. Heat generation per unit volume due to ohmic polarization is given by J square by sigma. Here sigma is material conductivity. Now comparing relative contribution of different kind of heat sources and sinks. Considering heat transfer analysis due to reaction part, different chemical reactions, electrochemical reaction contributes highest with accounting nearly half of contribution. Also steam reforming, which acts as a sink, accounts nearly one-fourth of heat transfer contribution. Coming to polarization part, major contribution is given by activation polarization, which accounts for one-sixth of total heat in SOFCs, as shown in table here. From now, my friend Shobit will continue the discussion of heat transfer via radiation.
Hello, now I am Shobit. I'm continuing the discussion on heat transfer, and we now come to the mode of heat transfer via radiation. So, first of all, why should radiation be considered in the SOFC model? It is because at elevated operating temperatures of SOFC, radiation heat transfer could become a dominant mode of heat transfer. Because of added complications in calculations, radiation mode of heat transfer is generally neglected. For typical operating temperatures of 900 to 1100 Kelvin and refractive index of YSG electrolyte equal to 1.8, it can be shown that over 90% of the emissive power is contained within the near to mid infrared spectral region. Radiation modeling. The radiative heat transfer equation was used to model radiation heat transfer and was solved using the discrete ordinate method. Discrete ordinate method is used to solve the above but is complex and computationally expensive. The solution of RTE depends upon approximation methods, the boundary conditions, and the radiation properties. Schwarzschild's two-flux approximation and Rosalind approximation are used to make calculations easier. Schwarzschild radiation model. The figure given below shows a schematic of two-dimensional enclosure used for validating the Schwarzschild radiation model. The temperature of the upper plate and the lower plate were fixed at 1200 and 800 Kelvin respectively, with the side walls being adiabatic. Studies were carried out for different optical thickness by varying the absorption coefficient of the enclosed medium. The simple solution of the radiative transfer equation for a gray isothermal non-scattering in the YSC 1D and plane parallel medium between two black walls at equal temperature is given by this equation, in which sigma is the Stephen-Boltzmann constant, T and Tw are absolute temperatures of the medium and walls, and tau is the optical thickness. For a medium confined between two isothermal parallel black plates at temperatures T top and T bottom and separated by a distance L, which is the thickness of the medium, the two flux model gives the radiative intensity as QR equal to C1 e raised to power 2kL plus C2 e raised to power minus 2kL, where C1 and C2 are given as follows. QR calculated above is coupled with the overall energy conservation by introducing the divergence of the radiated heat flux as a negative source term in the energy equation. Another approximation for calculating RTE is the Rosalind thermal conductivity. The presence of nickel doping makes the anode highly absorbing to thermal radiation, resulting in optical thickness much greater than 1. Radiative heat flux QR can be estimated with sufficient accuracy through Rosalind approximation as QR equal to minus K rad del T and K rad equal to 16n square sigma temp T raised to power 3 upon 3 beta R, where beta R is the Rosalind mean absorption coefficient, which is given as follows, and n lambda, IB lambda, and I lambda are the spectral index radiation of spectral index of refraction, spectral blackbody intensity, and spectral radiative intensity, respectively. Determining radiative properties. Absorption coefficient of YSZ electrolyte is given by Tr equal to e raised to power minus Kl. Tr is transitivity, K is absorption coefficient, and L the thickness of the medium. The multiplication of these two parameters K and L gives optical thickness. Let's move on to the results of simulations using the approximations. From graph of temperature versus channel length for different absorption coefficient, it can be seen that the larger the absorptive coefficient, lower the overall temperatures. The cases which model radiation heat exchange show lower wall temperatures in the cell. This makes physical sense because the hot upper walls radiate energy to cooler parts of the channel. Radiation effectively decreases the temperature gradients of the cell. The result obtained is significant because it shows that ignoring radiation heat transfer can result in the calculation temperature being over 32 degrees high. From the graph we can see that as the absorption coefficient increases, the overall temperature decreases. Inclusion of radiation effects resulted in a 1% and 0.9% drop in the temperature gradients at the interface anode electrolyte cathode respectively. Temperature distribution obtained at the anode electrolyte and cathode electrolyte interfaces for the cases with and without radiation in the electrolyte layer is shown below. From plot, it can be seen that effect of radiation is minimal and leads to a couple of degrees reduction in the interfacial temperature. The electrolyte is a semi-transparent material. This means that it can absorb, scatter, and emit thermal radiation. The radiation depends on the spectral absorption coefficient, refractive index, spectral scattering coefficient, and scattering phase function, emissivity, and reflectivity. Knowledge of these parameters as a function of temperature and wavelength are needed to predict the radiative heat transfer inside the SOFC electrodes and electrolyte. The figures show the simulation results obtained for the four different cases of optical thickness. This presents the temperature variation across the thickness of the liquid medium as predicted by the two flux approximation. Conclusion. Analysis of radiation heat transfer at electrolyte interfaces and certain physical properties of materials, including the cell system, such as absorption coefficient and refractive index of the YZ electrolyte, has been included before. According to the results for the geometry and material considered, the effect of radiative heat transfer within electrodes, electrolyte interfaces is small compared to the conductive heat transfer. The effect of radiative heat transfer within cathode electrolyte anode is respectively small compared to conductive heat transfer. The mean penetration distance for radiative heat transfer in nickel YZ anodes are in the order of nanometers. This means that radiation does not need to be considered in energy balances within the SOFCs for an intermediate temperature. If thermal radiation needs to be considered or not depend on several parameters such as temperature differences, materials, gas composition, gas pressure, fuel cell stack design, and wavelength, with or without radiative heat transfer within the electrolyte interfaces, the effect is negligible on the average cell temperature, which is around 1 to 0.9% as discussed earlier. Temperature difference across the electrolyte at temperatures relevant to SOFCs. This is not the case when the corrected radiative properties are used or for a very thin electrolyte, which must sustain much greater temperature gradients before radiation becomes significant. Although the results indicate that radiation within the electrolyte has little effect for the geometry and operating conditions used in the model, it cannot, in general, simply be neglected. Thank you.